Stars twinkle in the night sky, winking at us from across the universe. But have you ever wondered how they came to be? And what's going to happen to them when they die? Well, today we're going cosmically deep to learn about the incredible life cycle of a star. It all begins in space, where some clouds of gas and dust are humongous. These enormous globs of matter are known as molecular clouds. Molecular clouds come in many sizes, ranging from 1,000 to 10 million times the mass of our Sun. They're so big that they span as much as hundreds of light years, which is an astronomical unit of measurement equal to the distance light travels in 1 year. In fact, if you were to take a single molecular cloud and plop it down in Earth's suburbs, it would easily cover the entire city. Yikes! While studying these molecular clouds in the 1960s, scientists realized that far from being empty space, they actually contain more than 30 different chemical compounds, including methanol, ammonia, water, methane, and even some complex organic molecules. As a result, these massive gas giants got their name because they're the perfect place for chemistry to occur. But not just any kind of chemistry, the chemistry of life. That's why molecular clouds are sometimes called the building blocks of life. These clouds might seem awfully quiet, but they're teeming with activity. Within their chilly depths, gas particles bump into each other and clump together in loose groups, held aloft by the cloud's internal pressure and gravity. Over time, these clumps can collide with each other or continue collecting more matter. The result is a growing pocket of gas, with more mass than its neighbors. In fact, some of these pockets can get so dense that they'll start to collapse under their own weight. You see, gravity pulls all objects toward each other. The strength of this pull depends on two things: the mass of the object and how far away it is. The greater the mass, the stronger the gravitational attraction. But the farther away the object is, the weaker the pull. When you feel Earth's gravity, you're really feeling the collective gravity of all the planet's atoms. The closer you are to the center of the Earth, the more massive the chunk of planet you're near, so the stronger the gravitational pull. At the same time, you're also farther away from most of the Earth's mass. So in the end, the two effects balance out. But for a collapsing cloud of gas, things aren't so evenly balanced. As a massive cloud of gas begins to collapse, its mass comes closer together, increasing the gravitational pull towards the center. This increased gravitational force is stronger than the outward pressure that was keeping the cloud stable in the first place. Suddenly, the cloud's center is in freefall. It falls faster and faster as gravity drags everything towards the center. At this point, the only thing that can stop the cloud's collapse is more gas. If the cloud has enough mass, some of it will still be moving outwards against the pull of gravity. This additional gas slows the collapse, allowing other parts of the cloud to catch up. Eventually, the whole thing stabilizes into a ball of swirling gas and dust. This ball is called a protostar, a baby star being born. The intense gravitational forces squeezing the protostar will heat it up to unimaginable temperatures. Within the dense core, hydrogen nuclei collide with each other at high speeds, knocking electrons off their atoms. Now free to roam around, these negatively charged electrons combine with protons to make neutrons. In this way, two hydrogen nuclei can join together to make one helium nucleus, kicking off a tremendous release of energy. That's nuclear fusion, the process that powers our Sun and all the stars in the universe. Nuclear fusion creates the energy that makes stars shine. When nuclear fusion kicks into gear, the baby star is officially on its own, and astronomers call it a main sequence star. This is by far the longest phase of a star's life. Our Sun is roughly midway through this stage, which should give you an idea of how long it lasts. While in the main sequence, a star is mostly in equilibrium. Nuclear fusion balances gravity's tendency to crush the star. The star's luminosity, size, and temperature will slowly change over millions or billions of years. For example, the star will slowly use up its hydrogen fuel, which will cause its core to contract and heat up over time. This means that our Sun will get brighter and hotter as it continues to shine. But don't worry, by the time it reaches this stage, Earth won't be around to notice. How long a star spends in the main sequence depends on its mass. Stars with lower mass burn their fuel slower and are therefore longer lived. Red dwarfs, the smallest stars in the universe, may live for trillions of years, longer than the universe has currently existed. Meanwhile, massive stars must run through their fuel much faster to generate enough energy to keep from collapsing. The higher the mass, the shorter the lifespan. Massive stars will burn out in just a few million years. To put that in perspective, our Sun will likely live for another 10 billion years. So if you want to see a truly impressive star, you should probably check out one of those. But all stars, no matter their mass, follow this general path until their cores run out of hydrogen. When this happens, the energy produced by fusion can no longer balance gravity's tendency to pull the star inwards. What happens next depends strongly on the star's mass. Low-mass stars will see their cores begin to collapse, while their outer layers expand into a huge sphere. As the core gets smaller, it heats up to such high temperatures that fusion converts helium into carbon and the star becomes a red giant. Eventually, the helium fuel will run out, and the star will shed its outer layers, leaving behind a hot, dense core. This leaves a small stellar remnant called a white dwarf. Imagine taking the entire mass of the Sun and squeezing it down to something the size of Earth. This is how much space a white dwarf occupies. White dwarfs cool off slowly over billions of years and turn into black dwarfs, which are too cool to emit light. No black dwarfs have been discovered yet, because the youngest are roughly 10 billion years old. Now let's talk about what happens to high-mass stars. Once the hydrogen in the core is used up, fusion converts helium into carbon and oxygen. When the helium runs out, fusion continues, converting heavier elements into even heavier elements like neon, magnesium, and silicon. Each of these steps produces energy that prevents the core from collapsing, but each new fuel buys it less and less time. The whole process takes just a few million years. By the time the star fuses silicon into iron, it's almost out of time. The star has only a few days left to live. Fusion of iron into heavier elements requires energy instead of releasing it. This means the star's iron core begins to collapse under its own weight. As the core collapses, its temperature and pressure rise until suddenly, nuclear fusion kicks in again. Iron is fused into elements like nickel, zinc, and krypton. This sudden rebound pushes back against the core, halting its collapse and creating a shock wave that blasts outward through the star. This explosion is so powerful that it throws away most of the star's mass in a glorious display of fireworks known as a supernova. What's left behind after the explosion depends on the star's mass. If the original star was between 8 and 20 times the mass of the Sun, a supernova leaves behind a neutron star, an extremely dense ball of matter just a few miles wide. If the original star had more than 20 times the mass of the Sun, the core will collapse beyond the surface of a neutron star. Not even light can escape this region, so nothing can be observed directly. We can infer the presence of black holes by observing their gravity's effects on nearby matter. Once stars reach the end of their lives, they explode, scattering the building blocks of life into space. This material eventually collects into new molecular clouds. In this way, stars recycle their insides to make new generations of cosmic bodies. So the next time you look up into the night sky, remember that twinkling lights are not only stars, but stellar nurseries, graveyards, and furnaces.